Hello, my name is Caleb Lunsford. I'm a PhD student at Cornell University, and today I'll be presenting our work on the influence of toolpath design on the structural performance of 3D printed concrete gyroid walls. As a brief overview of content, first I'm going to be going over a background on our current interest in 3D PC walls and the gyroid geometry specifically. I'll explain how we designed our gyroids and the selection of our toolpaths that we used for our comparison. I'll go over the mix and printing parameters that allowed us to print these intricate geometries, go over the testing of our full-scale walls, both their numerical properties and the failure mechanisms, as well as some material tests we did in order to better understand how our walls performed. Finally, I'll combine those in our current up-to-date analysis and where we're moving on in the future. So as a very brief background, obviously there is increasing interest of 3D PC technology, with many startups already creating full-scale structures. Now these structures are generally made of wall elements, as walls are very easy to print with extrusion-based technology. But given the amount of work that's already being done, there's less research that has been published on wall elements, and even less being done on non-standard wall forms. There are examples such as the diamond wall shown here and the carp scale wall, but these tests, while interesting, were mainly to see the impact that aesthetic changes have on the structural performance of our wall. Thus, we found a gap in the research where there's no studies being done on the creation of complex wall shapes that have beneficial structural forms in some way. This then brings us to the gyroid. A gyroid is a triply periodic minimal surface, meaning that it is formed of a periodic lattice, such as this, that extends in all three principal directions, and it is optimized over this volume such that any change to this surface would lead to an increase in the area overall. The gyroid is just one of many triply periodic minimal surfaces, TPMSs. But among those, it has shown kind of the best performance when compared in all three directions. The gyroid isn't just a mathematical structure. There's also some indication of presence of gyroids in natural structures, such as the microstructure of bones and in butterfly wing scales. You can see gyroidal shapes. And as far as printing goes, the gyroid is already in use in micro and nanoscale printing and in small-scale plastic printing. This is largely because, as stated previously, the gyroid is extremely efficient under compression in all three directions. It's able to effectively distribute loads across its sinusoidal curves, shown here, and this allows it to carry a high load across a larger volume than would normally be possible, limiting the amount of material that is needed. There's actually already been some work to marry gyroids and concrete in a structural form. Examples include the use of plastic gyroids to reinforce concrete beams, or of using plastic printed molds to create cement paste gyroids for consideration, and even some early attempts to create 3D printed gyroid structures using sand as a removable structural support. However, all of these are very time-consuming and not particularly scalable, so our question became, would you be able to create a 3D PC gyroid wall directly without any supports? What would an efficient toolpath for such a wall look like? And how would the material properties of our mix impact the wall's performance? In a previous study, we'd already created some smaller-scale gyroid cubes, and we had sought to understand how extreme of a geometry we'd be able to print. We tested three major principal overhangs here, a 45-degree angle, a 56-degree angle, and a 63-degree angle in these cubes. And while for our 45-degree angle, we saw cracking fairly immediately, like at most 2 hours after our original print. But with both our 56-degree and 63-degree overhang angles, we didn't see any issues that we would normally associate with high overhangs in 3D printed concrete. So from this, we were able to find that our 56-degree angle was something we would be able to print with, and we moved to turn this initial structure into a full-scale wall that we'd then be able to test. As far as our toolpath selection, we decided to compare two major designs, a closed toolpath and an open toolpath. A closed toolpath is one where the beginning and end of each layer are at the same point, creating a fully closed circuit across each layer in the z-axis. This leads to a near constant interlayer delay between the different layers, as the extrusion nozzle is reaching the same point at roughly the same time for each separate layer. This does, however, require more material, as we then need this back wall section to connect what would be the end point to the start point otherwise. An open toolpath, however, does not have this requirement, as the start and end can be at different points along the layer. This obviously uses less material, as it's no longer necessary to connect the two, and they're able to be on disparate corners. However, this does lead to a variable interlayer delay across the toolpath, as you can see here. In these two diagrams are the green is the start of our toolpath of the layer, and the red is the end of our toolpath of the layer. And obviously, the closed toolpath, it's very consistent throughout with only minor changes, but the open toolpath is obviously oscillating back and forth, as every other layer, it needs to move back on itself. Now, both of these are able to to create the same structure and reach the same envelope. They can create the same size and scale wall. So our main question then is between these two, which would be stronger and which would be a more efficient toolpath to print the wall? In order to make this print possible, we had to develop a printable mix in-house. This mix has a water to cement ratio of 0.35. Its cementitious paste content is 52%. That's both the cement powder and the SEMs being used. Of that mix, our SEMs are 30% content by weight, and we had a maximum aggregate size of 2 millimeters. All of this was to reach a flow diameter of 17 centimeters with an open time of 30 minutes. Both of these are very important, as they are necessary in order to flow through our entire system, which I will now show. Our full system consists of a 7-axis ABB robot arm with an X-tree print head and feed equipment attached. So mixing starts here at this drum mixer, moves into this shearing vane, which then, as it waits to then be pumped through our hoses up to our nozzle, and then placed for deposition. This is a 2-part system, so that accelerator is added right at this nozzle, our accelerator being a aluminum sulfate. And what this allows for is us to keep our 30-minute open time throughout this entire process, which is necessary, but then to achieve sufficient stiffness and buildability as it is deposited. We create 50 to 70 liter batches at a time and add them to our system. And for each of our walls, it took roughly an hour and 45 minutes to print. So for these walls, we managed to get 2 printed, one for the closed toolpath and one for the open toolpath. And after 28 days of curing in accordance with ACI 308, we then performed a uniaxial compression testing as shown here. This testing is displacement controlled at 1.27 millimeters per minute, and both the quantitative low displacement curves were recorded, as well as the failure of how each wall behaved. First, I'll explain how our closed toolpath wall performed under testing. After initial loading, we saw cracks beginning to form at these top overhangs here. And as loading continued, that then led to a failure of this overhang, which led to the wholesale break off of a large section of this sinusoidal curve structure here. Continued loading showed lateral expansion of this failure, eventually removing the entire top sinusoidal section as well as all of the overhangs. And only one crack was seen in other sections below kind of this line here in these other sinusoidal sections. We suspect that the reason for this is because of these overhangs specifically. The overhangs are due to a cutoff in the geometry, as we can see lower down, given the periodic nature of the gyroid, it's just a repeat over and over again. But where we cut it off here, you can see we cut it off there, there, there. And what this leads to is, instead of the gyroid being able to distribute across its entire geometry, we suspect there are stress concentrations building up in these overhangs that then lead to failure at the top of the wall before the rest of the wall can be properly loaded and lead to failure. Our open toolpath wall, however, actually behaved in a very different manner. There is still cracking that can be seen in these upper overhangs, but now we're seeing significant cracks originating from one side of the entire wall and spreading down the gyroid nature. continued loading led to the failure of a large portion of the wall here, which then led to the failure of the entire system fairly rapidly afterwards. There's still indication of the top overhangs failing during this loading process, but very clearly there is something different about the open toolpath that is leading to this new failure mechanism that our closed toolpath was not experiencing. Looking at our quantitative results, they largely agree with this assertion. Our closed toolpath wall was able to reach a maximum load of 880 kilonewtons before having its initial failure at the top, and then this progressive failure of the lateral expansion of the progressive failure was shown here in this section until we stopped the test. The open toolpath wall, however, only managed to load up to 480 kilonewtons before reaching both its initial failure and then the second failure, as shown previously. Now, obviously, our closed toolpath wall did perform better. It reached a higher load, but this isn't necessarily that surprising, as it requires more material to create the closed toolpath wall. What is interesting, however, is looking at our capacity to weight ratios for the two walls. We reach a capacity to weight ratio of 1.83 for our closed toolpath, while only reaching 1.26 for our open toolpath. If it was just a case of more material being able to support a larger load, then we would expect that the capacity to weight ratios for the two walls were similar. So that suggests that our open toolpath wall not only failed in a different manner, but the manner of failure is caused by a weakness in the open toolpath wall that isn't present in the closed gyroid. In order to further examine the tests shown here, we did a series of small-scale compression testing. These tests were taken from these smaller beams that we were then able to cut into 50 millimeter cubes. Each of these prints has the same parameters as our larger scale gyroids, the same print speed, the same flow rate, the same time between layers, the same layer length, so that they are a representative sample of our entire walls. And for testing, we tested the anisotropic properties of the mix, showing three different loading areas, which we denoted in accordance with their orientation to the toolpath. So we have orientation 1, which is perpendicular to the toolpath, orientation 2, which is lateral to the toolpath, and orientation 3, which is lateral to the toolpath direction. For each of these orientations, we tested 6 cubes in both open and closed toolpaths with additional cast cubes for comparison. Here are the results of these tests, which was also done at 28-day strength. And as we can clearly see, the cast samples performed the best, both in terms of their compressive strength and in terms of their coefficient of variation, the highest strength and the lowest variation, which is largely to be expected. The fact that we're only seeing a maximum of 28% reduction in strength across all of our different tests does situate us well within the rest of the body of literature and show that our cubes are performing well. In reference to how our different tests perform, our closed toolpath cubes first show a slight anisotropic properties with a 10% reduction in strength from our parallel orientation 3 tool loading to our perpendicular orientation 1 loading. But given that our mix is relatively strong, reaching up to 60 megapascals and 60 to 70 megapascals, 10% isn't that noticeable as far as anisotropic properties go. What is interesting, however, is the difference between the closed toolpath and the open toolpath loading. Our open toolpath, specifically the open toolpath lateral loading cubes, had a significant drop in strength when compared both across the open toolpath, across the open samples, and to its comparison to the similar closed samples. This is a greater than 20% reduction in strength, which is significantly more noticeable, and is also correlated with a significantly higher coefficient of variation, which is nearly double that of even the second highest coefficient of variation of the closed toolpath lateral loaded samples. From this, we can reasonably look to see that it is possible that the failure here and the high variation and the lower strength is what may have caused our failure of the walls. So looking at the reason that this may have occurred, obviously, as 3D printing doesn't require any additional formwork, the lack of confinement during the printing can lead to the mortar spreading out laterally along this direction. Literature has shown that the orientation to our lateral loading can be weak due to this mortar spreading, as the spreading doesn't allow for as much strength buildup, and that this can be impacted by the interlayer delay. Obviously, if an interlayer delay is too long, then one layer will start setting before the other layer, leading to cold joints. But if the delay is too short, then the first layer won't have time to set properly, and the layer that is placed on top of it will cause additional deformation, which will lead to lower strength. This is especially important for our setup, because the way our prints occur is that one layer pushes down slightly on the other layer as it is being printed. This is extremely useful to have high interlayer bond. As you can see from this sample, if there was any failure between the layers, we'd see some striation here along the layer path, but we're not seeing any. So that's good for our mix most of the time, but for our open toolpath samples specifically, places of high variation between different layers, as was shown in our toolpath previously, may have led to failure of one layer due to additional loading before it was able to set fully. Taken together with our wall results, we can then hypothesize a possible relation between the weakness of our compression samples and the difference in failure methods between our two walls. Obviously, the gyroid toolpath is the gyroid shape in and of itself can distribute loading in a non-standard way, which will lead to this lateral loading that we saw. And the fact that lateral loading has shown a weakness in our open samples and our open cube samples can lead to additional weakness and failure kind of in this way that we saw from our full toolpath, from our full gyroid wall as shown. So from this, what we were able to determine is that we had successful printing of our gyroid shapes with our 3D PC elements, that our overhang design and the cutoff of our gyroids can limit its maximum strength, as the closed toolpath wall failed in a way that showed that it was just stress concentrations and not the entire wall in and of itself. So there's still room for us to optimize there. That the toolpath we choose will impact our performance, with the open toolpath failing in a different way and being significantly weaker than our closed toolpath. And from all of these, our next steps are that we're looking to construct a finite element model that takes into account our differences in toolpaths so that we can further test our two different walls in numerical modeling and relate that to how the actual walls themselves performed. And finally, a testing of a third wall has already been printed, and testing of it will be underway shortly. And with additional tests of the fresh state properties of our mix, which have not been fully documented, in order to fully explore the trends that we have observed so far. On behalf of everyone at our lab, thank you very much for listening, and I'll now be ready to take questions.